So, some upcoming dates while you're getting out your own notes for this. We will have a formative quiz on April 17th. That is Thursday of next week. Okay? And then we're off of school the 18th and the 21st. Okay? We will have the test on this unit the 23rd, which is the following Wednesday. Okay? Then we're going to review 3 days for your final, and you will be taking your semester 2 NTC final on April 30th and May 1st. Okay? So that is the final that then will go in as your final for second semester, the first part of your final for second semester. And it will also then combine with your first semester final to go towards your NTC final. But we'll have plenty of time in May to tell you what grade you have for NTC and so on and so on. Okay? So that's coming up on the horizon. Okay? So let's get at it. So algebraically, we can look at a complex number, z. Typically, we call our complex numbers z. So you'll see a lot of z sub 1, z sub 2, z sub 3. Those are just different complex numbers. Okay? So algebraically, we call our complex number a plus bi. That's the standard form. It's also called rectangular form. It's also called just a complex number form. Okay? A plus bi. An example of that would be negative 2 plus 3i. Okay? That's a complex number. It's got a real part that is negative 2. It's got a complex part that is 3i. It's got an imaginary part that is 3i. To combine the real part and the imaginary part, and you get the complex number. Okay? When we graph this, or if we were to graph this, we would graph this on something called the complex plane. Now, the complex plane is very similar to your Cartesian coordinate system, xy, okay? But the complex plane has the horizontal values being the real parts. Oops, that should be an L. It's the real parts of the complex number. And the vertical axis is the imaginary. Axes. Okay. So the point, or the complex number, negative 2 plus 3i, could be written here as an ordered pair, a comma b, if we were to graph it in the complex plane. That would be negative 2 comma 3, which would be 1 and 2, 1 and 2 and 3. So that would be kind of right up in there. That's where z would end up. Okay? Real part is your x, imaginary part is your y, and then we go from there. Any questions on that before we go to the next slide? The trigonometric form of a complex number. So now we're going to make z be 2 minus 5i. So let's first start with a sketch. The sketch is going to be, we are going to go to the point, we're going to graph the point 2 comma negative 5 on the complex plane. Okay? So if I'm graphing the point 2 comma negative 5 on the complex plane, that puts me down here with z. Do we agree with that? Okay? Each and every complex number is a certain distance from the origin, And we call that distance in the complex number world. Oops, tap the brakes. Better color in here for it. We call that distance r from the origin. And it's on a directed ray theta, which is a trig angle. Okay? We're not dealing with an airplane. We're not dealing with a ship. We don't see the word navigation. We don't see the word bearing. So this is a trig angle. Okay? We can figure out that r and that theta very easily, knowing what we know about things. Okay? So, for instance, r here, we can do it all right here. Okay? So if this is my origin, r would be this distance right there. How would I be able to find my r value? Pythagorean theorem, so what would it be? Okay, or using my actual numbers, I could go that r here is the square root of 2 squared plus negative 5 squared, right? 2 squared is 4, negative 5 squared is 25. So r then is square root of 29. Questions on that? Okay. My theta is going to start here because it's a trig angle and go around to there in the trig angle direction. How am I going to go about finding actual theta? Great. Okay, so let's start with the reference angle first. So that would be theta prime. And theta prime is going to be what? Inverse tangent of 5 over 2. Again, remembering that we drop the negative signs. Okay. What do we get for a reference angle there, rounded to 3 decimal places? Okay, but we are in which quadrant? We're in quadrant 4. So that means actual theta is going to be what? How'd you get it? 360 minus my reference angle. So that means actual theta here is 291.801 degrees. Would you concur with that? Yes? Grant, put your phone away. So, how can we find r and theta in general given a complex number? Well, given the complex number in the complex plane, that also means that this is equal to a comma b in terms of an ordered pair for it. So how would we find r then? Square root?
Yeah.
Yes, ma'am. Square root of a squared plus b squared. Okay? How would we find theta? But that's going to be my reference angle, correct? B over A, you said? What's the kicker? What's the catch? So we got to drop the negative signs? Where have we seen all this before? Oops. It's all the stuff that we've been doing for the last couple of weeks, right? Really hasn't changed. The only thing that's changed now is instead of you finding actual distances and speeds and direction angles, now we're just finding direction angles and complex numbers, the lengths of complex numbers, okay? Or the magnitudes of complex numbers. Okay? And then from there, if we're in quadrant 1, theta is my reference angle. If we are in quadrant 2, theta is 180 minus the reference angle. If we're in quadrant 3, 180 plus the reference angle. And if we're in quadrant 4, 360 minus the reference angle. All good. Okay? So, I'm just going to randomly select here an A and a B. Right? Now, I can make a right triangle out of that. And then this would be my actual theta. Do we all agree with such? Yeah? Okay? All right? Let's call this blue side X. Let's call this red side Y. What would I call the green side? I call it what? R. I would call it R. Okay? So knowing that, what would X be equal to, or what would Y be equal to? Again, this is a right triangle. Why does making it a right triangle become uber important? No? Because what? We can use SOHCAHTOA now, right? Okay? So if I want to solve for X, what am I going to use? I don't know what X is, I don't know what Y is. The only thing I know is R and theta. For X, for cosine? Okay? So X here, or I should say the cosine of theta is going to be X over R. Do we agree with that? Using ka of SOHCAHTOA. Which means then that X here is going to be R cosine of theta. Yes? Okay. What am I going to use to find Y? Sine. Okay. So the sine of theta is Y over R, which means then that Y is going to be R sine of theta. Do you agree? Okay. Well, I could also say here, I could say that instead of x, what could I call this? I could call that a, because that's my a in my a comma b, right? Which makes, then I can go over here and I can say, oh, instead of x, I can call that a. What can I call in place of y? B. So in place of y here now, I could say that that's B. With me on that? Okay. The reason that I say that, or the reason that we made those changes, is because now we can get standard form of a complex number into the generalized trig form. So if my standard complex number is a plus bi, and we just said that z is equal to a from up above, a was r cosine of theta, and b from up above was r sine of theta. We get that, right? Do I really need those sets of parentheses? No, right? Okay. So this is really just r cosine of theta plus r sine of theta times I. Can I do anything with that? Make it look prettier? No? It's the dreaded F word. What can I factor out? R. I can factor out an R. Yeah. So the trig form of my complex number is going to be R times the quantity of what? Cosine theta plus. Now here's where we're going to tweak it a little bit, because now R is out of the way. So now we can put I first. So it's R times the quantity cosine theta plus I sine theta. With me? Let's dive into some here now. We want to write z here in trig form. So if I want to write it in trig form, I need to know two things. I need to know r, and I need to know theta. Okay? So we just did this one, correct? This was the second example that we did when we were talking about the trigonometric form, right? What did we have for an r value before? Square root of 29, okay, because it's 2 squared plus negative 5 squared gets me the square root of 29. We also did the theta value. Does anybody remember what the theta value was? 291.081? 801? Okay? So the trig form of this complex number would be z, that's the name of it, the name doesn't change. My r value would be the square root of 29. Then I would have the cosine of 291.801 degrees plus I sine of 291.801 degrees. And that, ladies and gentlemen, is the trig form of the standard form of the ordered pair form. Those are the three forms now that we can have of a complex number. Standard form or rectangular form, ordered pair form, trig form. Okay? So once again, standard form here would be A plus BI. Ordered pair form would be A comma B. And trig form would be R cosine of theta plus I sine of theta. Now, a little shortcut that we're telling you about today, but we're not letting you use it today. Okay? You get to start using this shortcut tomorrow. Okay? R cosine plus I sine. We, because we're lazy, mathematicians by nature are lazy, we call this RCIS theta. Because the angle's going to be the same always. Okay? So you need to know your R, and the CIS is cosine I sine. So that's where CIS comes from. You get to use this after today. Okay? And that just shortens up your writing a little bit. Because later on, we're going to get to roots. And so if we're taking the seventh root of a complex number, that means you're going to have to write down cosine of an angle plus I sine of an angle 7 different times. Because there's 7 different roots for the seventh root. So that's where this comes in, to make it easier. Shorter. Okay? All right? Let's dive into one now here. -3 plus 4i is my complex number. I would like us to find the trig form of it. Okay? First thing that we need to find with trig form is we need to find our r value. Square root of -3 squared plus 4 squared. Okay? -3 squared, 9. 4 squared, 16. 9 plus 16, 25. Square root of 25. Square root of 25. 5. So we got an R value here of 5. Bennett giving everybody a start. I know we're in tight quarters now. Not everybody's used to it yet. But I do like this setup. Oh, do I like this setup. Okay? What's the other thing we got to find? We got to find theta. Okay? Now, since we're not in quadrant number 1, that means we're actually going to have to find theta prime first. That's going to be the inverse tangent of 4/3. What do we get for a reference angle? Which quadrant is this complex number actually in? It's actually in quadrant number 2, so that means that actual theta here is going to be 180 degrees minus the reference angle. So that means that actual theta here is going to be how much? 126.870 degrees. Good with me so far? Okay? So the trig form of this complex number z then would be 5 times the cosine of 126.870 degrees plus I, that's a really, I went hard on the loop there, plus I sine of 126.870 degrees. Tomorrow, you'll just get to say 5 CIS 126.870. Good? Try that one. So the first thing is we got to find R. R is going to be the square root of negative 2 squared plus negative 2 square root of 3 squared. Negative 2 squared is 4. Negative 2 square roots of 3 squared is 12. 4 plus 12 is 16. The square root of 16 is 4. We good so far? Sometimes those squaring of square roots gets you a little bit. Okay. Then we also need to find our reference angle theta, which means we're going to have to find theta prime, or our reference angle, I should say. So then that's going to be the inverse tangent of 2 square roots of 3 over 2, which is just, I believe that is 60 degrees, if I'm not mistaken. Yes? Okay. So that is 60 degrees. Since this complex number is in quadrant 3, it's negative, negative, then that means actual theta is going to be 180 degrees plus my reference angle, or 240 degrees. Are we all good with that? Yes? Okay. So the trig form of z here in this case would be 4 times the cosine of 240 degrees plus I times the sine of 240 degrees. Yes? Questions, comments, concerns? Try that one. I like this one. Because this is 0 plus 8I for that one. So that gives me an R value here of 8. That gives me a theta of 90 degrees. Okay? Okay? If you need more confirmation of that, if we graph it on the complex plane, 0 is my A, 8 is my B, so that's straight up 8 on the imaginary axis. So there's where the 8 distance comes from, there's where the 90 degrees comes from. Okay? So then this z value here should be 8 cosine of 90 plus I sine of 90. Very hard to do the inverse tangent on this one because you'd get an undefined because it's 90 degrees. Try that one. I get an R value of 10. I get a reference angle value of 30 degrees. Since this is in quadrant 3, theta is 180 degrees plus my reference angle, so I get 210 for my actual theta. So my complex number in trig form is 10 cosine of 210 plus I sine of 210. Yes, ma'am.
How am I getting this in? Like, I want to know how much really
Because you need to put your 5 square roots of 3 in an extra set of parentheses. So, no, they're not. So I need a parenthesis 5 square roots of 3, close, gives you 30. Yep. So, because what your calculator was doing, it was doing the 5 divided by the 5 as 1, then multiplying it by the square root of 3, which got you the inverse tangent of the square root of 3, which is 60. But you wanted the square root of 3 on the bottom. Okay? Now, going the other way. So now we're in trig form. We want to get back into standard form, rectangular form, A plus BI form. Okay, so this is really 8 cosine of 135 degrees plus I times the sine of 135 degrees. Agree with me on that? Just writing it out in full-fledged form instead of the shortened form? Yes? So if I want to go into A plus BI, the only thing that I need to do is I need to distribute this 8 into both of those. Okay? So this is going to be, then, 8 cosine of 135 degrees plus 8I times the sine of 135 degrees. Do we concur with that? Okay. Well, what's the value of the cosine of 135 degrees? Negative root 2 over 2? What is the value of the sine of 135? Root 2 over 2? Eight times negative square root of 2, then divided by 2. This one, this first blue one. Negative 4 square roots of 2. Eight times I times square root of 2 divided by 2. 4I square roots of 2. And there is your standard form. Or if you chose to write it too, you could always go like that. Oops, tap the brakes. I was still on the negative 4 square roots of 2 plus 4 square roots of 2 in parentheses I, then it truly is a plus bi. But I would also accept this one. Okay? You try example 2 as our last example of the day. Oops, I forgot the I. Agree? Z is 6i. Now, truthfully, I'm going to actually back this up a little bit. Truthfully, Z here in standard form would be 0 plus 6i. If it's in complex form and it's in standard rectangular form. Okay? We'd have 0 plus 6i there because we have to have an A and a B. If we just wrote 6i, then that's just the imaginary number. Okay? I'm about to hand out for you a homework packet for this unit. Okay? On the first page, the front side, which you can do today, even though Schmeling screwed up, he pulled the Schmeling and we didn't recognize it until after we printed them off. He was going to make all 4 of these down here not be in shorthand notation, but he only changed the first one instead of all 4 of them. So, okay? So these will be handed out on the front page, no shorthand. After the first page, then it can be shorthand all you want. Take one down, pass it around. Take one down, pass it around. Take one down, pass it around.